The story of the hydrogen bomb begins not with a bang, but with a flicker of terrifying possibility. In the crucible of World War II, the Manhattan Project gathered the world's greatest minds to unlock the atom's core. Their success, and the devastating use of atomic bombs on Hiroshima and Nagasaki, proved humanity could wield the power of nuclear fission. But for some, this was merely the first step. The end of the war did not bring peace, but a new, colder conflict. When the Soviet Union detonated its own atomic bomb in 1949, a new and horrifying chapter of the arms race began. In the United States, influential physicists like Edward Teller argued that a far greater weapon was not just possible, but necessary. They called it the super, a weapon that would work not by splitting heavy atoms apart, but by fusing light ones together, mimicking the very process that powers the sun. The result was a design of diabolical elegance. The core concept, known as the Teller-Ulam design, used the immense radiation from a fission bomb, an atomic bomb, as a trigger. The A-bomb would act as a matchstick, creating the millions of degrees of heat and crushing pressures needed to ignite the fusion fuel, unleashing 1,000 times more energy. After a series of tests, the United States prepared for the ultimate demonstration. The goal was to create a dry-fuel thermonuclear weapon, one that used a solid compound, lithium deuteride, making it small and light enough to be delivered by a bomber. The device was codenamed Shrimp, and the test was named Castle Bravo. On March 1, 1954, at Bikini Atoll in the Pacific, Shrimp was detonated. A silent, blinding flash gave way to a monstrous sun that bloomed over the ocean. The fireball swelled to over 4 miles wide, boiling the sea itself and vaporizing the test island and 2 others nearby. But in that flash of creation, there was a terrible miscalculation. Scientists had assumed that only one isotope of the lithium fuel would participate in the reaction. They were wrong. A second, seemingly stable isotope also reacted, unexpectedly breeding more fusion fuel and nearly tripling the bomb's power. A planned 6-megaton device became a staggering 15-megaton blast, 1,000 times more powerful than the bomb that destroyed Hiroshima. The consequences were immediate and horrifying. The massive fireball dredged up tons of pulverized, irradiated coral from the seabed, blasting it into the stratosphere. This created a vast, deadly cloud of radioactive fallout. 100 miles away, the crew of a Japanese fishing boat, the Daigo Fukuryu Maru, or Lucky Dragon, was showered in a strange white ash they called death ash. They had no idea they were being lethally poisoned. The radioactive cloud spread across the globe, detected in Australia, India, Japan, and the United States, proving nowhere on Earth was safe from the consequences. Castle Bravo was more than a test. It was a horrifying lesson. The genie of thermonuclear fire was out of the bottle, and the world would forever live in its shadow. For most of human history, our vision of the cosmos was surprisingly small. The Milky Way galaxy, with its brilliant river of stars, was thought to be the entire universe, a vast, solitary island of stars adrift in an endless, empty void. Dotted among its stars were faint, blurry patches of light called nebulae, believed to be swirling clouds of gas or solar systems in the process of formation. The most famous of these was the Great Andromeda Nebula. To the naked eye, it was a faint smudge. Through a telescope, a beautiful, mysterious spiral cloud. For centuries, astronomers debated its true nature. Was this nebula a nearby cloud of gas, a cradle for new stars within our own cosmic home? Or was it something far more profound? The debate came to a head in the early 1920s. The key to solving the mystery would be a new cosmic yardstick discovered by the brilliant astronomer Henrietta Swan Leavitt. She had found that a certain type of star, called a Cepheid variable, pulses at a rate directly related to its true, intrinsic brightness. They were perfect, standard candles. If you know how bright a light truly is, You can tell how far away it is just by seeing how dim it appears. Using the powerful new 100-inch Hooker telescope at Mount Wilson Observatory, an astronomer named Edwin Hubble began a meticulous study of the Andromeda Nebula. Night after night he aimed the telescope at Andromeda, painstakingly capturing its faint light on photographic plates. Then he found it, a single pulsing point of light within the nebula, a Cepheid variable. Hubble measured its pulse rate to determine its true brightness, then compared that to how dim it appeared. The calculation that followed would forever change humanity's place in the universe. The numbers were staggering. Andromeda wasn't thousands of light years away, nestled within our galaxy. It was nearly 1 million light years distant. It couldn't possibly be inside our galaxy. It was an island universe of its own, just as vast and magnificent as our own Milky Way, populated with hundreds of billions of its own stars. In an instant, the known universe didn't just get bigger. It shattered and reformed into something incomprehensibly vast. The walls of our cosmic home came crashing down. We were not alone in an island universe. We were just one island in an endless cosmic ocean, filled with countless other galaxies, stretching out to the limits of our sight. That single discovery transformed cosmology forever. Today, we know there are hundreds of billions, perhaps even trillions, of galaxies in the observable universe. And it all began with one man, one telescope, and one faint fuzzy patch of light that taught us our true place in the cosmos.